just like we would do if there was some recursive case. We know in our case that we don't need to do it when we're doing it by hand, but in order for everything to be extremely uniform and facilitate some proofs, the default generation actually uses a size. If you look at it a bit, it doesn't actually use the size. So in case it's 0, it does one thing. In case it's not 0, it does exactly the same thing. What is that thing? Well, in our generator, we match on t and produce a natural number or a Boolean. What does this do? Well, half the time, it's going to match on t if its Booleans fail, if its natural numbers succeed. And the other half the time, it's going to match on t if it's a Boolean, generate a Boolean, otherwise fail. However, we're using backtrack. So if you pick the wrong match, you're just going to fall through to the correct one. So if you, in the end, the distribution that is produced is actually identical to the one we have here. It's just a more roundabout way of doing it. At this point, I usually get a question that is, but why don't you just optimize it away? And we could, for this case and for many cases, do a few such optimizations. If we see that that we don't need the size to terminate, we can just ignore it. If we see that the match, that you can hoist the matches out of the backtrack and combine some cases together, you could do it. The reason we haven't is that Quickcheck also has a way of deriving proofs that these generators are complete at the same time. So while actually the exactly same code that produces this can also produce a proof that this generator is correct. And by correct, I mean it only produces things that satisfy the relation you said, and all the things that satisfy the relation you said can be produced. And the only way we can do that so far is by having this very straightforward structure to produce those proofs at the same time. And I don't think I have it here, but it would be interesting to show you a proof like that at some point, because someone asked me offline if you can actually do proofs of completeness by hand for the generators you write. And the answer is yes, but don't do it. The proof term for this is probably around 1,000 lines. Okay. So I've been using, there are a few type classes on that slide that I'm using. And you can already use those in your development. So for example, there is gen size such that. Naming is subject to change in the next few days while we discuss it with Benjamin. So it has one method, arbitrary such that, that's what ST stands for, that takes a natural number and produces an optional A, where the convention should be that the A satisfies this P that you get along with. And there's also an unsized variant and some convenient notation so that you don't have to use signify exactly the A and the type class instance, but you want to be able to signify what the property P is. So let's see that in action. Here's a conditional property. Before the type class hackery that we did for the last slide, if you wanted to test this property, Quickcheck would generate a random x, generate a random y, test that x equals y, and then test the conclusion of the property. If you now go and run Quickcheck on the conditional property, you'll note that it has 0 discards. That means that we can do some type class hackery, and the Quickcheck knows to use a conditional generator for x equals y if it has one. So it will generate only x's that are equal to y in order to do this, because clearly getting 0 discards by generating 2 random numbers and testing that they're equal is practically impossible if you were to actually do that. And I think that's all I have for today. Yep, so any questions?
after you define your own finite maps data type, are you aware of any developments that use the finite maps library of the standard library in Mach and this QuickCheck feasible to use?
I have personally used the finite maps library for an earlier project, and you can easily test it. You cannot easily derive things for it. That's the problem. Whenever you have things that are wrapped by modules, it's much harder to derive things for them because that has to be done internally. From the outside, you usually are able to use its API to produce things or show things or things like that. And in fact, an earlier the iteration of this talk last year was using a module type for maps, like exactly that. I don't think it was using fmaps, but it was using the list map version. And there were a few hoops you had to go through. For example, there is in this example, we just const the thing at the top of the list when we set something. If you wanted to use the map version, wait, not this example. It's the no. Here, this example where you're creating a context, you can just combine the range, and that's the list map, and you know it. However, if you wanted to use the module version, you can't just return a list. You have to fold through this and insert all elements in the list, right? So there are slight annoyances like that that you probably have to do because you don't have access to the actual representation outside of the module. However, as a module developer, you could easily use QuickCheck inside and export the functions that you need. So yeah, good question.